Welcome to the deep dive. Today, we're plunging into a really fascinating area of artificial intelligence.
hmm
Think about how often when you're tackling a tricky problem, you maybe sketch something out,
Yeah.
like maybe draw a diagram for geometry, or map out a workflow, or even just plot some data points to see a pattern.
Yeah, absolutely. We do it all the time.
These visual aids, they feel pretty central to how we as humans reason and find solutions.
It,
They help us see things more clearly.
they really do. And, that very human ability using visuals to think, that's actually been a huge challenge for AI, a really fundamental one. We have these vision language models, VLMs, and they're getting quite good at, say, answering questions about an image you show them.
Right.
But their internal thinking, if you will, often stays purely text-based.
Just words.
Just words. So the ability for these models to explicitly create and then use visual aids while they're problem solving, this idea called visual chain of thought or visual crescimol, that's been a major open challenge. And it's really vital, both for boosting AI performance where that visual intuition matters and also, frankly, for making the AI's reasoning process easier for us to understand, more transparent.
So what's holding it back?
The big hurdles have generally been, well, a lack of really good high-quality training data and also the fact that models don't just naturally do this visual cushious stuff well right out of the box.
Okay, so that sets the stage. And this is where I gather the focus of our deep dive comes in.
It is. Researchers from places like Columbia, University of Maryland, USC, NYU, they've developed something they're calling Zebra-CoT.
Zebra-CoT.
It's a new data set aimed squarely at this problem.
So today we're going to unpack this Zebra-CoT dataset. We'll explore what it is, how they put it together, which sounds like quite a task, and what kind of impact it's having on developing AI that can reason multimodally with both text and images. Okay, let's get into it then. What exactly is Zebra-CoT? What makes it different, this breakthrough for thinking visually?
Well, what's really interesting about Zebra-CoT is its scale and its design. It's a large data set, over 182,000 samples. But crucially, each sample isn't just, an image and some text. It contains these logically coherent, interleaved text-image reasoning traces.
Interleaved traces, so like step-by-step thinking shown with both words and pictures working together.
That's the idea. Think of it as showing the work visually and textually. This is quite different from a lot of earlier large data sets. Those could often be noisy or maybe just had image-text pairs without that clear, structured reasoning process built in. Zebra-CoT is specifically curated to train models to generate useful visual aids as they work through a problem.
That makes a lot of sense. The quality and the structure of the data seem key. So what kinds of problems does Zebra-CoT actually prepare these models for? What sort of visual thinking are we talking about enabling here?
It covers a really impressive range, actually. They've structured it around 4 major categories spanning 18 different subdomains, so broad coverage.
4 categories. Like what?
Okay, so first there's scientific questions. This is a big one. It includes things like geometry.
Like my earlier example.
Right. And here they actually take plotting code, say, from math problems and turn it into actual rendered diagrams. So the model sees the visual steps, both for the problem setup and the solution.
So it learns to see the geometry problem unfolding.
Kind of, yeah. It sees the explicit visual reasoning chain. Same category includes physics problems, using things like free body diagrams for forces or motion diagrams for kinematics.
Visualizing forces in movement.
Exactly. Also chemistry, showing molecular structures, even algorithmic problem solving using visual aids for abstract concepts, and graph algorithms too.
Okay, that's science.
Okay.
What else?
Then you have 2D visual reasoning. Think about tasks like visual search, where a model might learn to draw bounding boxes or sort of zoom in visually, or visual jigsaw puzzles.
Jigsaw puzzles, like filling in missing pieces.
Yeah, exactly. Filling in maybe 1 to 4 missing pieces, sometimes rectangles, sometimes irregular shapes, into an image. It forces the model to think about spatial arrangement, patterns, colors.
That sounds quite intuitive, actually. What about 3D? That seems like a big step up.
It is. That's a third category, 3D visual reasoning. This includes things like embodied planning for robots,
Meaning?
teaching a model to generate step-by-step plans for how a robot might navigate or interact within a 3D space, like figuring out high-level actions.
So planning a path or how to grab something.
Right. Or robot planning for very precise manipulation tasks. How exactly does an arm or gripper need to move? It also covers things like 3D multi-hop object counting, which involves understanding how a scene changes from different viewpoints.
Visualizing the scene from different angles.
Yeah, understanding transformations and imagining those perspectives.
And the fourth category?
The fourth is visual logic and strategic games. This includes things like mazes, pathfinding, navigation planning, and chess. They use mid-game positions from actual rated games on lichess.
How does that work visually?
Well, the dataset helps train models to simulate future moves by visualizing the consequences of different candidate moves, showing the resulting board state for each potential move independently.
So it's not just calculation, it's seeing the potential outcomes, developing tactical awareness visually.
That's the aim. This category also includes various visual logic puzzles, think Tetris, Raven's progressive matrices, which are all about pattern recognition.
Ah, RPM tests, right. Pure visual inference.
Exactly, and things like the abstraction and reasoning corpus, ARC-AGI, checkers, even ciphers where the encoding steps are visualized.
Wow, okay. That is a truly comprehensive set of challenges. It covers so much ground. Which brings me back to the how. Given this huge range and the focus on really high-quality structured data, how on earth did the researchers actually build Zebra-CoT? It sounds like a monumental effort.
It really does, and it raises that key question about data curation. They used a couple of main strategies. First, they went out and sourced high-quality problems that already existed in the real world. Things from online resources, math competitions, physics challenges, coding platforms, those chess data sets we mentioned.
Okay, using existing challenging problems.
Right. And from those, they had to extract and carefully clean up the raw reasoning traces, the step-by-step solutions that might have been present. The second strategy was generating synthetic examples, sometimes using parametric Python templates to create structured problems, other times crafting new examples using real images.
So a mix of real-world extraction and synthetic generation.
Yes, but here's the really crucial part. They didn't just stop there. They used advanced VLMs themselves, specifically mentioning Gemini 2.5 and GPT 4.1 to enhance these raw traces.
Using AI to improve the training data for AI.
Sort of, yeah. They'd feed the raw text and any associated images into these powerful models and basically ask them to output a refined text trace, but with very precise placeholders indicating exactly where a generated image should go.
Ah, so ensuring the text and the metals were tightly linked, logically coherent.
Precisely. Making sure the references between the text steps and the visual aids were crystal clear. They also had a filtering step to remove any invalid cases, like if multiple placeholders accidentally pointed to the same image or something wasn't logical.
Meticulous work.
Very meticulous. And this whole multi-stage process is what yielded that final data set of over 182,000 high-quality traces. It created this resource where models could learn genuinely meaningful connections between reasoning steps, text, and generated visuals.
Okay, so they've built this impressive data set. What does it actually do? What does this mean for the capabilities of AI models? Are we seeing real improvements from training on Zebra-CoT?
Yes, the results they reported are quite compelling. They definitely suggest a significant step forward. For example, they took a model called Anol 7B, a general language model, and fine-tuned it using the Zebra-CoT 2 training data.
Yeah.
Its accuracy on the Zebra-CoT test set jumped quite notably by 12 percentage points, going from about 4.2% up to 16.9%.
Okay, 16.9% might still sound low overall, but that jump from 4% is substantial, right?
Yeah.
It suggests it went from barely guessing to having some real capability on these complex visual reasoning tasks.
That's a fair way to put it. It shows the model started to genuinely grasp tasks needing that visual chain of thought. And it wasn't just on their own test set. Fine-tuning on Zebra-CoT also led to an average improvement of nearly 5% across 7 other challenging VLM benchmarks. These are standard tests used in the field.
So broader benefits too.
Right. And on one specific visual logic benchmark, the gain was even higher, over 13%. So it shows the data set helps across different kinds of visual reasoning challenges.
That's interesting. But you mentioned earlier that a key challenge was getting models to generate these visuals themselves. Does Zebra-CoT help with that?
That's perhaps the most significant finding, actually. They also fine-tuned another model, Bagel 7B. Now, this model originally couldn't generate interleaved text and images. It just wasn't built for that.
Okay.
But after fine-tuning on Zebra-CoT, it actually gained the ability to inherently generate high-quality visual chains of thought during its own reasoning.
Wow. So it learned not just to understand the visual steps, but to create them as part of its process.
Exactly. It developed that intrinsic capability. It wasn't just using visuals provided to it. It started creating its own internal visual aids to help it reason through the problem. That's a pretty big deal.
That does sound like a game changer. Moving from interpreting visuals to actively using visualization as a reasoning tool.
It really points to the effectiveness of the data set in instilling these visual reasoning skills. And importantly, they've open sourced everything, the data set, the fine-tuned models, to encourage more research and evaluation in the community.
That's great to hear. So wrapping up our deep dive today, Zebra-CoT seems like a really fascinating step forward in AI. We've explored how this big, carefully built data set is essentially teaching machines to think using both words and images together, much more like how we humans often approach complex problems.
I think that's right. Zebra-CoT feels like a crucial, maybe foundational step towards AI systems that can reason visually much more naturally, as intuitively as we might sketch something out or use our spatial sense to figure things out.
It definitely makes you reflect, doesn't it? How much our own intelligence, our own way of understanding the world, is really tangled up with our ability to visualize, to connect things visually, to almost literally see the answer sometimes.
It's a deep question, and this kind of research certainly brings it to the forefront.